A 570-ton machine standing on two concrete piers is holding a full bridge span in the air. Below it, nothing but a gap between piers. The gantry lifts, slides, lowers, and walks itself to the next span, thousands of times in a row, until an entire high-speed railway exists on concrete stilts. See how a machine with no road beneath it keeps building the road ahead. Wait for the reveal near the very end. Look up. That red machine standing on two concrete piers is holding a full section of bridge in the air. The launching gantry moves span by span without touching the ground, carrying loads close to 900 tons. The workers up there act like they do this every day, because they do. Watch the drone pull back and the trick shows itself. The gantry sits at one point on the viaduct while a finished railway stretches behind it for kilometers. This is not one bridge being built. It is a production line that happens to be 30 feet in the air. Now zoom in on what it is actually carrying. The yellow gantry crawls forward, a full concrete span hanging under its main beam, around 25 meters long, several hundred tons on the hook. You would not want to be the one who dropped it. Here is the part most people never think about. Bridges used to be built one small piece at a time, right at the site, with formwork and rebar and concrete pours happening in the open air. That works fine when the schedule allows years of patient stacking. High-speed rail does not. The precast span method flips the process. Each span is cast in a factory-style yard, cured under controlled conditions, then hauled out to the alignment as a finished product. The gantry becomes the last step of an assembly line. Pier goes up, span comes in, span drops into place. Then the whole rig walks itself forward and asks for the next one, like a very slow, very heavy commuter. And this is why the elevated approach exists in the first place. Most high-speed railway track in China does not sit on the ground. It sits on viaducts, 30 to 50 feet up, running for hundreds of kilometers with piers spaced almost identically the whole way. The reason is simple. A bullet train needs an alignment that is nearly flat, straight, and free of level crossings. Farmland, rivers, roads, villages, and small hills all sit in the way. Building a bridge over everything solves all those problems at once and takes less land than you would guess. So the real challenge stops being how tall or how long. It becomes how fast, how repeatable, and how precise. Every span placed on the viaduct is nearly identical to the one before it. Yard, transporter, gantry, batching plant, crew, all synced. But before that gantry can lay anything down, those spans have to come from somewhere. That place looks less like a construction site and more like a factory with a very serious concrete habit. Every span the gantry places came from somewhere. That gantry, roughly 92 meters long and around 570 tons, has already laid nearly 300 full spans in one direction and is now heading back the other way. It only works because there is a yard behind it, running around the clock, keeping the spans coming. And that yard is not a construction site. It is a factory that forgot to put a roof on. Each finished span here runs about 40 meters long and weighs around 970 tons. To keep the gantry fed, the yard has to turn out roughly 300 of these things every month. Think about that for a second. A concrete object heavier than a fully loaded 747, rolling out the door every 3 or 4 hours, every day, for years. That is not construction pace. That is manufacturing pace, only heavier. The yard has its own batching plant, its own casting beds, its own molds, and its own gantry cranes just for shuffling things around inside. Here is the part hiding under every span. A casting bed is a long, flat steel platform where the piece takes shape. At one end sits the press-dressing anchorage. Steel strands run down the full length of the bed and get pulled tight before any concrete goes in. That is what lets the finished span carry a train later without cracking. Now watch a span come together inside the yard. Rebar cages get tied on jigs so every bar sits in the right position. Cages get lifted by gantry cranes and dropped inside the outer mold. Inner shutters slide in from the ends, closing off the hollow shape. Concrete pumps pour tons at a time while workers guide the flow around every corner. The yard runs multiple molds in parallel and stacks finished spans by order. Miss one step and the delay ripples down every mold behind it. The real trick with a box girder is what you cannot see from outside. The span is hollow. That empty core keeps a 40-meter piece from doubling its own weight. The hollow shape stays extremely stiff against twisting, which is exactly what a train doing 300 kilometers per hour wants under its wheels. A big mold is not just a small mold scaled up. Hydraulic cylinders open and close the sidewalls. Workers clean, lay reinforcement, thread strands, close the mold, then pour. Try doing that by hand at bridge scale, and the crew would be old before the first pour finished. Concrete going into a 970-ton span cannot be a mystery mix. Every batch has a target for water, cement, sand, gravel, and admixtures. The control system logs each pour so nothing drifts. Get one batch wrong and you have baked the error into something you cannot exactly send back to the kitchen. Order matters more than people think. Aggregate goes in first, moisture gets measured, cement drops, water flows, admixtures follow. Blades sweep the whole load until it moves like heavy syrup. Change the order and the concrete comes out weaker without telling you why. Before a launching machine can lift a span, that span has to survive the lift. Steel strands are tensioned after the concrete cures. Then grout is pumped into the ducts to lock the strands in place and protect them from corrosion. The final step is sealing the anchors with protective caps, the same post-tensioning principle used across bridges, whether they carry highways or high-speed rail. Every span sitting in the storage yard started as a pour that could not be rushed. Pump trucks feed a hose crew that walks the concrete around the mold, corner by corner, while vibrators drop into the mix to shake out trapped air. Miss a pocket and you have a hidden weak spot that will not show up until years later at the worst possible moment. The reason inspection matters so much at the end is because the pour itself does not give you a second chance. Once concrete sets in the wrong place, the fix is either grinding, patching, or in bad cases scrapping the whole span. On a 970-ton piece, none of those options are fun to explain to the site manager. Every pour gets logged, batch numbers, temperature, slump, cylinder tests. If a problem shows up in the finished span, the crew can trace it back to the exact truck that poured that exact section on that exact day. A storage yard is not chaos. Finished spans get stacked in a specific order that matches the installation schedule out on the alignment. Gantry cranes move them into rows. First span out is the first span the transporter grabs, and nobody is picking through the yard looking for the right one. This is what leaving the yard actually looks like. Two heavy transporters roll under a span from opposite ends and lock into a coupled formation. Each unit carries about 500 tons on its own. Combined, the pair can move roughly 1,000 tons, which comfortably covers this 32.6 meter, 800-ton box girder. Look at the tires, then look at them again. The transporter runs on hundreds of small wheels arranged in tight rows, spreading the load across the road so no one spot takes too much pressure. Even so, the crew lays down thick steel plates along parts of the route, because past deliveries chewed the pavement anyway. Rubber under 800 tons does not exactly ask permission before rearranging asphalt. The steering is where these machines get almost graceful. Every wheel turns independently, so the pair can crab sideways, pivot in place, or thread through curves that stop a regular truck cold. At the Y-shaped junction, the pair stops, the driver walks from the front cab to the rear cab, and the whole formation reverses direction without turning around. Try that with your car sometime. Once the transporter reaches the launching gantry waiting up on the viaduct, the delivery chain has done its job. The rest of the schedule depends on what one machine, standing on two piers, can do with 1,000 tons hanging under its beam. No matter the girder shape, delivery has to be flawless from start to end. A 44-meter T-girder rolling 5 kilometers on public roads is a full operation of its own. Police escorts, traffic control, roadside spotters, and slow, careful, steady progress from start to finish along the entire route. And sometimes the supply route runs through a tunnel. The transporter carrying an 800-ton span, about 12.6 meters wide, has to pass through a tunnel that is roughly 13.5 meters wide. That leaves less than half a meter of clearance on each side. The word we are looking for is snug. The crew guides the transporter in slowly, watching both walls at once. Anything worse than a straight line means scraping concrete, and neither the tunnel nor the span is going to enjoy that. Every entry gets rehearsed before it happens. Once the span reaches the gantry, the placement is only the beginning. What makes this whole system worth building is what happens right after. Installing a full-span box girder for a 350 km/h railway is a challenge. The gantry lowers its rear support onto the last installed span. The transporter creeps in with the span underneath. The gantry hooks the 4 lifting points, takes the load, and holds it steady in the air. Then the trolley on the main girder starts moving. It slides the entire span forward over the empty gap between 2 piers. Below, there is nothing but air until it reaches the pier bearings on the far side. And the whole operation, from the moment the transporter arrives to the moment the span sits on the bearings, takes about 50 minutes. That is the timing that lets a viaduct advance at 3 or 4 spans per day when the yard, the transporter, and the gantry are all in sync. Lose one link in that chain, and the schedule bleeds hours. But the launching gantry is only as fast as its supply line, and that supply line runs across the already finished viaduct. The transporter carrying an 800-ton span rolls at 4 to 5 km/h, using the completed deck as its highway. The road on top of the finished spans is barely wide enough for the transporter itself. 2 operators run the coupled units, one front, one rear. When another transporter comes the other way after dropping off its span, both formations pass each other on the deck. Not exactly the moment you want to check your phone. At this pace, the transporter is not really a truck anymore. It is a slow, floating platform. The point is control, not speed. When the load weighs 800 tons and the bridge underneath is also carrying its own weight, plus the transporter, going slow is what keeps everything inside the design envelope. Occasionally, the gantry itself has to turn around. When a section of viaduct is complete and the next section starts in the opposite direction, the machine cannot just spin on the spot. It is more than 70 meters long, so it does a very slow, very patient K-turn using every inch of the open ground available. Forward, back, adjust the angle. Forward, back, adjust again. 13 full round trips is not unusual for one U-turn. Total time to complete the whole turn, roughly 40 minutes. Which sounds slow until you remember this is a 570-ton machine changing direction with 0 damage to a bridge full of finished box girders. Special transition supports get added to the transporter to help move the gantry more efficiently during the swap, because otherwise the reposition would eat into the erection schedule for days. The moment the span sits on the bearings, the crew starts working on the next cycle before the current one has even cooled. Slings come off. Bearing contact gets checked. Surveyors verify the final elevation. The trolley on the main girder retracts to its home position. Then the gantry starts to walk. The front leg lifts off the pier it was standing on and extends forward to the next pier. The rear leg follows, sliding along the finished span behind it. The whole 570-ton machine moves itself across the gap it just filled, one leg at a time, without any outside crane assisting. Meanwhile, back at the yard, another span is already being cast. Out on the delivery route, another transporter is already rolling. By the time the gantry is in position over the new empty span, the next full-span box girder is arriving at its rear. The cycle does not restart. It never stopped. Watch a time lapse of one of these machines from above, and you can see the whole pattern in a few seconds. The launching gantry sits over an empty span. The transporter arrives, the gantry lifts, the trolley slides the beam forward, the beam lowers onto bearings. Then the machine walks itself one span forward. A new empty gap appears in front of it. The transporter comes back with the next beam. The pattern repeats span after span, day after day, kilometer after kilometer. On a well-run project, 3 or 4 spans a day is normal. Some sites push higher. The bridge grows in the drone footage like somebody is drawing it in fast forward with a very heavy pencil. The point of the whole system is not one impressive lift. It is the ability to do that lift, correctly, on schedule, hundreds of times in a row. That is the difference between a bridge and a viaduct. The idea of feeding a bridge from a precast yard is not specific to high-speed rail. Bahrain used the same core arrangement for a coastal causeway. Segments cast on the ground, hauled to the alignment, then lifted by a launching gantry that walks along the bridge as it grows. The advantage matters in busy areas. Instead of parking cranes in the middle of city traffic for months, most of the work happens off-site in the casting yard. Fewer workers on the elevated structure, less interference with the highway below, and faster erection once the machine gets rolling. The construction site basically shrinks to the size of one crawling machine. The trade-off is that everything has to be planned to the millimeter. Segments only fit together correctly if they were cast in exactly the right sequence, with the exact geometry the design called for. Not every high-speed rail viaduct gets built the same way. Some use cast-in-place concrete poured right on the alignment, with heavy formwork and scaffolding standing underneath the whole time. That approach fits short signature structures like arched viaducts crossing a busy highway, where each span is unique enough that repeating a launching cycle would not really save the crew much time or trouble at all. Across a long alignment, you will see multiple methods used side by side. Grade separations, cast-in-place viaducts, and precast girder viaducts each fit different terrain and schedule demands. The 6,000-foot Hanford Viaduct alone uses 286 columns. The scale is not about one bridge. It is about hundreds of them, back to back, running for miles. And so the launching gantry keeps walking, span after span, until an entire high-speed rail line stands on concrete legs across the country. Some people look at this and see raw power. Others see something more interesting. The moment construction stopped being a construction site and started being a factory that happens to be 12 kilometers long. Every finished span becomes the platform for the next one. What looks slow from a distance is actually a production line measured in bridges instead of products. By the time the last span is set, thousands of tons of concrete have been placed with millimeter-level accuracy. That is how hundreds of kilometers of elevated railway take shape without stopping the world underneath. The question this raises is worth thinking about. Should more of our infrastructure be built this way, turned into precast, repeatable, factory-grade work? Or does that trade too much local craftsmanship for speed? Drop your take in the comments. Curious what side of that argument you land on. Hit subscribe. More heavy industrial stories are on the way, and none of them are going to be small. See you. Take care.